Hello, this is Graham. It's Thursday, the 18th of July, and I thought I would talk about the quark diagrams that I have. So this is a classic Feynman diagram. It's a UDD, which is a up, down, down quark, and the configuration changes to go from a neutron to a proton, and the decay gives off a tau neutrino and an electron charge. The modification to the Feynman diagram on a one-dimensional lattice, which looks like this. So we'll just add a bit of a scribble. Here we go. So if this is a section of space-time, okay, what we do is we take that and we wrap it into this shape, okay. And obviously, if you have enough of these, you end up with a surface. This is zoomed right in at the Planck scale. And what we're doing is we're saying that that this surface represents, as a two-dimensional surface, this represents the behavior of a one-dimensional core sample of what's going on inside the atom. Okay, so what we have is we have the quarks, although they change their configuration, okay, what doesn't happen is that the electromagnetics stay the same. So there's no real change in that one. But this one, okay, what you have is that there is a magnetic field which is suddenly released. There is no longer a gravity well. This gravity well we will very quickly go and have a look at. It is described here as the charge of the acceleration, okay, which is mediated by R naught. There's a video on Maxwell's equations here, but this is what we're looking at. This decays into QV. So we're going from QA to QV. And because of that, what's happening is something's happened. The gravitational well that was holding the up quark here is released, and it turns into an electric field moment. It's almost like this is an electric field, and what you can do with the electric field is you can wrap it around like this, so that it becomes magnetic rather than an electric, which is why this here is a steering force, okay, in loops, and this is an accelerating force. So this is all about QV, and this is all about QA. Okay, you have your photon comes off, you have a tau neutrino and your charge, because the quark triplets inside the atom itself, the nucleus, the up quark loses its gravitational pull, and it is released, and it becomes an escape velocity E. And the mathematics for that are labelled here. So if you look at the very top, you can see you've got P to N. When a proton is turned into a neutron, which is the process that goes on in a magnetar or neutron star or a black hole at the extreme, if you reverse it, you've got a neutron decaying into a proton. Now, the mathematical description of that is that the 4 bullet points are what describe normal fractional charge in the standard model, but what we have got here is we can then sum them up. We can sum those three vectors to give you equation 4.3 and 4.4. One is capital pi, which is the sum, which is the product, and that can be also plugged into the standard model, because if A is obviously equal to unity, then A cubed becomes 1, and that is consistent with the 4th bullet point, which says here which fit the standard model. The bit that's different is if you rotate this diagram for the positive charge part, then what happens is you end up with the neutron, and this now means that in the complex, by placing this A cubed business, if you put that as a complex number, or rather it's a complex vector pair, then what you end up with is the magnetic field as a complex component, and if you sum that to this one, you have a complex number which describes the fractional magnetic field and the fractional charge. Now, these are not the monopoles. Okay, don't get that confused with the monopole, Maxwell's monopoles. That's not what these are. We'll talk about that one in another video. we'll now move over to these diagrams because they're coloured. It's because we're now in quantum chromodynamics, because the charge, you have colour charge, and we need to take that in consideration. What's nice about this is that the x and the y axes can be represented here because they're orthogonal to each other. What we have is we have a nice PDF probability distribution where the green curve shows you that at the 0 point, you're most likely, okay, to find a proton, which is an electric field plus a fractional magnetic field. And if we're looking at the imaginary axis, what we're most likely going to find here is a neutron. That's it. We're just going to find a neutron. And so the angle theta here is an indicator of what the probability is inside this kind of little P loop. You can see it's like a bent infinity. What we find is that it's the area. The shaded area is the most probability over time. So theta is time, and that's 25, 30 minutes for decay time. The magnitudes, of course, E plus B, you need to divide by 2, and the same with the B plus B. And of course, B plus B divided by 2 is just simply B, but E plus B divided by 2 actually gives you fractional charge and fractional magnetic field. And hence this diagram. For me, it's the magnetic field is the long way around. It's what's owed, and of course that is an indicator for space-time. The magnetic field is an indicator that's stored in space-time to say, hey, there was some offset of conservation of acceleration. Gravitational acceleration energy is owed somewhere, and for the electric field, obviously that's to say that special relativity for velocity is owed somewhere. I think that's it, really. Just very quickly, is that when u1 is added to u2, it becomes 0, and you end up with a vector that's got x plus a. Obviously, this point here is your 0 up there, and that is a vector on the real axis. And this is where the real is cancelled out, and you end up with a value on the imaginary axis. So what you have is you basically have your charge and your magnetic moment on a two-dimensional surface representing a one-dimensional vector in space-time. Okay, so if we had 6 of these diagrams, they would be in quaternion form to give you a surface to a vector. So those two surfaces are a surface because this is our surface, okay? And what we have is we've got the imaginary in this direction and we have the real in that direction. It doesn't really matter which way around you do it. And how we do that is we take this one-dimensional core sample of space-time. So this could be planet Earth, and this could be the sun over here, and you want to do a transmission line model. Then you take that core sample of space-time in meters, where your meters are sort of divisions like this, and you take this whole core sample as a transmission line, and what you do is you wrap it into this shape. And what you're doing then is you're saying that if you're going to hop over all of these, then what you're doing is you are traveling along the magnetic field, okay? But if you're traveling in little hops around here, then you're doing the electric field. Obviously, you've got plus and minus, and B is obviously going backwards and forwards. The wonderful thing about doing it like this is that not only do you get a topological surface, but remember that, that magnetic fields are represented like this, aren't they? They get compressed inside there like that. And those are your magnetic field lines. If you take that core sample of space and you say, I'm going to do this, and what happens is that magnetic field then, oh, I've done that wrong, it doesn't matter, it's very difficult to do that. There you go. That magnetic field is now contained inside. And that's very nice for the model of a neutron. Thank you very much for listening.